Hi everyone, I'm Andrea Gorgi, a PhD student at Simne, enrolled in a European project called GECKO. Today I'm going to introduce you briefly to my research line, which title is The Isogeometric Analysis and the Shifted Boundary Method in Contact Mechanics. A contact problem in general is any problem where two or more objects will enter in contact during the simulation, and the physics is governed by a set of governing equations, in general structural mechanics equations, plus decoupling with a thermal problem eventually for each of the bodies involved. And additionally, we would have to solve a set of inequality constraints to impose the non-penetrability of the objects, and in the case they are needed, the frictional laws. The most common issues in the context of computational contact mechanics are the treatment of these inequality constraints, which is generally done by Lagrange multipliers and penalty methods, the loop over the contact boundary to compute the correct contact interface, which is not known a priori, and the correct representation of the contact boundary. This last point in particular is fundamental to obtain feasible results and compute the exact contact interface, and you can see how much you would have to refine the mesh, in the case of the finite element method with two circular objects, to correctly capture the complexity of the geometry and compute feasible results. This is exactly where the isogeometric analysis comes into play. Isogeometric analysis is basically an alternative to the finite element method, where we choose as basis functions the same functions used by the CAD modelers to draw the geometry. These functions are fractional B-splines, and this means that for our very coarser mesh, we are able to we will have our computational domain exactly coincident with our true domain from the CAD. Everything works through a projection from what we call parameter space, where the elements are simple quadrilateral ones, into the physical space, where these elements are deformed into curvilinear elements to capture the complexity of our geometries. In terms of convergence, in general, isogeometric analysis shows very similar results compared to the finite element method with the use of the same order of the basis functions. But the game changer in this case is the possibility with the isogeometric analysis to increase easily and in a robust way the order of the basis functions, gaining a lot in terms of accuracy of the solution and in terms of the degrees of freedom required by the solver to compute that solution. And of course, much lower computational times. Unfortunately, the standard isogeometric analysis still has some limitations, in particular for moving or deformed objects or for complex geometries, where the mapping in this case is very hard and time-consuming to compute. And this is exactly what motivates us into moving to immersed boundaries and immersed methods. In particular, the shifted boundary method, which is a method introduced by Professor Guglielmo Scovazzi, works with an immersed geometry in the sense that we do not require the mesh to perfectly capture the complexity of our geometries, but this won't be necessary in this case because we will impose the boundary condition to our computational domain by a projection from the true boundary to the computational one by the use of a Taylor expansion term. To explain better myself, this is the case of an IGA body fit scenario with a circle. You can see how, in general, an element is deformed from the parameter space to the physical one. And this is the case of the shifted boundary method, where we can even choose the parameter space to be exactly coincident with the physical one. You can see how in this case we are not capturing the exact geometry, we're not fitting the exact geometry of the circle, but it's not necessary because we will impose the boundary conditions by a projection from the true domain with these green dots to the computational boundary via a Taylor expansion. Here I present the results in terms of convergence. You can see how they both show optimal results and very similar results. Of course, the body fit scenario will overperform a little better than the shifted boundary scenario, but still the shifted boundary shows optimal results, and the difference in terms of accuracy is very, very low compared to the potential and flexibility that these methods provides. We have implemented this method for both 2-dimensional and 3-dimensional cases with both inner holes and external cuts, and it always performs in an optimal way. Everything was implemented in the custom multiphysics software, which is the software used in SIMNet. Regarding the current progress for the contact, we are able to solve, for example, a simple patch test with IGA, with a coarse mesh, and in this case, the result is very, very similar to the one obtained with the finite element method in Kratos, which is very, very promising, but we hope to move as soon as possible to the case of immersed objects in the contact with immersed objects with isogeometric analysis and shifted boundary method. So that would be all. Please check out our recent paper on isogeometric analysis and shifted boundary method written together with Nicola Antonelli, which is another PhD student here in SIMNet, also enrolled in the GECKO project. So thank you for watching, and bye.